modalities of treatment, we are talking about CRRT, which basically are talking about CVVH. This is called as continuous veno-venous hemofiltration. Then you have CVVHD, which basically is continuous veno-venous hemodialysis, and then you have the last one, which is CVVHDF, which is continuous veno-venous hemodiafiltrations. Now you say veno-venous always now. There is also arteriovenous. So you can actually just connect the arterial line, and you can connect a venous line. The artery will work as a pump. The artery will work as a pump. Put a filter in the middle and attach the filter to an effluent bag. So you can have femoral vein. You can have it like this. You can have the artery connected to a filter. The artery connected to the filter, and then from here whatever is going back will go back into the vein. Okay, then there will be an opening over here called as effluent. So that will come out from here. You understand? But you know that this is going to be very inferior because you don't have a pump here. You don't have a pump to move this. So if you don't have a CRRT machine, you may want to use it. I have done it. Okay, I have done it where you apply it and dialysis kind of works. At least your dialysis modality will work, diffusion will work. If somehow the filtration will work, some filtration will work. Okay. So CABHD, but we never do CABHD. We've gone out, we've come out of the CABHD mode now. We are usually using our pump derived CVVH, CVVHD, CVVHDF, right? And as I told you, this is related to convective mode of clearance. This is related to diffusive mode of clearance, and this is a combined thing. Okay. What you must also understand is when I am saying convection, is we are giving fluid from outside. Ultrafiltrate can be done in any of these modalities. That is different. Ultrafiltrate can be done in any of these modalities. Ultrafiltration is different. It is removal of water. Clear? Ultrafiltration is removal of pure water from the body. So if you have tomorrow slow continuous ultrafiltration, I am only removing water out of the body. That is ultrafiltration. Just removal of water outside the body. Clear on this? This principle is clear? Now let me take the example of the first case. Let's take the example of the first case. Let's take CVVH. So I am just drawing your filter here. This is a filter. Okay. I am putting blood from here. That's QB. Okay. I am taking blood out from here. That is QB dash. Okay. And now what do I want to do? What is more happening over here? I am going to add a replacement fluid. And as we discussed the other day, the replacement fluid could be either pre-filter or post-filter. So I can have a replacement fluid here, or I can have a replacement fluid here. Okay. All these machines, all these filters will have a small port from which it will go into the effluent bag. All these machines will have, all these filters will have a port, artery, vein, a small area where you can actually attach filtrate, and there will be a fourth area where you can attach dialysate. So each of these filters will be like this. So you can attach the artery, you can attach the venous back to the body. There will be a small area where you can attach the dialysate. You can attach a dialysate which will go counter current, which will flow counter current, and you will have a replacement fluid. That goes effluent fluid that comes out from here into the bag. Clear on this? Every filter is going to be like this. Clear? Every filter is going to be like this. When you are not using the effluent, when you are not using the dialysate, this will be off. But every filter is going to be like this only. Clear on this? Am I clear till now? So I have just recreated this filter here. I have recreated this filter by saying that this is my filter. This is my QB, my blood flow. This is my blood coming out, the venous side. This is my replacement fluid. I have put it pre-filter, and I have put my effluent over here. Whatever treatment modality we talk about, how much of our effluent comes inside, that is your dose per hour. Understood?
Effluent comes outside.
How much effluent comes outside, that ml per kilogram per hour is your dose. is your dose. Now let us see what is the effluent that is coming outside. Let us see what is the effluent that is coming outside. So let's take the modality of CVVH. CVVH. What am I adding inside? Replacement fluid. That is not going inside the body. No, convective है वो. तो पानी के बाहर आ रहा है. It is helping the middle molecules and small molecules to go across the membrane. So what is coming here is actually a replacement fluid. And as I told you, any of these modalities, you can actually add a UF. You can actually add a UF, which is like the urine. It's like the urine. I can add a UF. So I may be able to add a UF here. Like here I'm adding a UF. I can add a UF here. Okay. So at the end of the day, what is my effluent here? The replacement fluid plus that's my effluent. Clear on this? Now let us take an example of we have started the dose at 150 ml per minute and we have put the replacement fluid at 1000 ml per hour. Okay, on the pump the blood flow will be in ml per minute and the replacement and dialysate fluid will be ml per hour. Okay, so now I have put it 1000 ml per hour and I have now added a 200 ml of UF. Say 200 ml UF added कर दिया. What is my effluent here? 1000 plus 200, right? So this is 1200 ml per hour. Yes, I want to make it ml per hour. And what is my dose in? Per kg per hour. So now let me make this 70 kilos individual. Okay, 1200 ml divided by 70. 7 ones are 7, 7 ones are 7, 8, 70. So this is 70 ml per kilogram per hour. This is my dose. You got my dose now? Is this dose adequate?
25 to 35.
Exactly. Okay. Understood this? Clear? Now let me change the modality for you now. This is for CVVH. Okay. I'm going to change the modality and I'm going to make dialysate. Okay. I'm going to make a dialysate now. I'm going to add it as CVVHD. So what do I remove from here? Nikhil, come. What do you want to remove from here?
Replacement fluid.
Remove. So I'll do it for you. So you want to remove the replacement fluid. He's right. So sit down. So I'm going to replace the replacement fluid. I'll remove my replacement fluid. What do I need to add? Dialysate. So let me add dialysate. So it is counter current now. So I'm adding a dialysate that goes counter current. Where is this dialysate going to go? This 1000 ml per hour. It is going to go where? Effluent. It's going to go to the effluent. So I'm going to get all this thing into the effluent over here. Right? Now what is the dose of CRRT CVVHD here? QD plus whatever if I am adding UF. Whatever UF that I am adding through here will be my dose. This is my dose of CVVHD. Clear? Again I divide it by the body weight and I have my answers. You understood? Understood this much? We'll go to some case scenarios after some time. Some basic cases will make you understand this all. Clear this? Okay. Now, what will happen if I want to do now? If I want to do CVVHDF, I have my effluent here, and I want to do CVVHDF. What do I need to do? So, add a replacement fluid. So I can add my replacement fluid here, which I call as QR. To talk exactly like how CRRT will be talked at. Okay. What else I want here? Dialysate. So counter current?
QD.
Very good. QD. Now what is my effluent? Sorry?
QR
plus QD plus
QR plus QD plus UF if I have added some UF here. This is my dose. Now let us take our patients that we have. I am giving a regular dose. My regular dose is usually what? And what is the regular dose that I am putting in on the machine? Kanchan?
1000 ml dialysate, 1000 ml replacement.
Okay. So 1000 ml dialysate plus 1000 ml replacement plus 100 ml UF. This is what I normally put. to start with. If I don't want to, I start like this. 2100
30 हो जाएगा.
divided by 70. How much is it?
13.
What is the dose we require? Simple. Dose समझा तुम लोगों? हाँ? Understood the dose? Any queries till now? No. So where does this blood pump come? So our problem with this machine is the fact that we want to ensure that this doesn't get clotted. See, CRRT machine will never work in the first 5-6 hours. It is starting to work at 12 hours and you will get complete approximation at 24 hours. So at complete approximation, what am I going to have? The BUN that is coming from here, the urea that is there in this side will be equal to the urea here, because it is going to approximate. Are you understanding? Because it's going to approximate, it's going to easily diffuse because it's a fast diffusible molecule, it's a small molecule. My urea here and my urea here will actually be the same. I can actually figure out whether my machine is working well by looking at this. I'll just send effluent urea and I will send effluent blood urea. Both of them have to divide by, it should be 1. If it is 1, it means this is optimally working. Right? Are you understanding? Because urea is easily, you can monitor it. Clear on this? I want it to be optimally working because my CRRT is going to start work at 12 hours to 24 hours, because it is going for this to occur, it will be 12 to 24 hours. You understand? There are nothing is going to happen. First 2 hours nothing is going to happen. It is going to occur at 12 to 24 hours. It's a slow modality. It's an extremely slow modality, and that's why I need to ensure that the filter works very, very well. That means the filter does not clot. For the filter not to clot, there are few equations that you must remember. Okay. So what you must remember is my blood pump should be 2 to 2.5 times my dialysate flow. If I'm going to use CVVHD. So now let's take the example of 1000. So 1000 into 2 is how much? My dialysis is 1000, no? So 1000 into 2 is how much? 2000. QB is 150. If I'm putting ml per minute into 60, कितना हो गया?
9,000.
More than 2 to 2.5 times? 2000 versus? So if I put this like this, in no way my filter will get clotted. Clear?
So is this irrespective of that citrate pumps?
Irrespective of everything. Well, of course, that is also part of it. But the chances of it clotting is almost unlikely if I use this. Why am I telling you this? Because समझ लो कल तुम्हारा बीपी गिर गया और तुमने इसको 20-30 ml कर दिया, 30 ml कर दिया. Now let us multiply this 30 into 60. कितना हो गया?
1800.
It is less than 2.5 because I need to have at least 2500, 2000 to 2500 here. I make this 30. What will happen to my filter? समझ में आया? So you don't reduce the blood pump flow just because the BP is dropped, because the filter will clot. So this equation you must remember, 2.5 times the dialysate. You understood, Sachin? So when you're starting also, you must start like that. When you're starting your dialysis machine, you don't start at 50 and 1000. You start at 50 and 1000, what is going to happen? The chances of filter clotting is high, no? 50 into 6,
9.
and say you take 800 over here into 2.5, 8 5 is 40, 8 is 70, 90, 20, more than that, no?
4,000. It will be 4,000.
It will be 4,000 and this will be barely 3,000. So 3,000 versus 4,000. Will the filter clot? Yes, it will. Are you understanding? So you must remember, when I'm starting my CRRT machine, I must ensure that my blood pump flow is 2 to 2.5 times my dialysate flow. Simple principle, very simple principle. This is in case of CVVHD. Now what happens when there is CVVHDF, or for that matter CVVH? If there is CVVH, okay, that is this part of the story, then here there is another equation. The equation is, if we are giving this pre-filter, the blood pump flow should be more than 6 times the replacement fluid. Clear? It should be more than 6 times the replacement fluids. So, are you understanding this? Clear? So, let us take the example of our circuit, 150 ml per minute. So 150 ml per minute will be 150 into blood pump flow 60 हो गया ना ये 150 ml per minute per hour कितना हो गया 9 liters. Now let's take 1000 our replacement fluid into 6 कितना हो गया
6,000.
Is it more than 6 times? It is. It is more than 6 times. This is solving my problem.
150 पे रखा उसको तो
समझ में आ रहा है? Are you understanding what I am saying? So, in a modality where we are going to use convection, there is hemofiltration. I want to keep my blood pump flow 6 times of the replacement flow, more than 6 times of the replacement flow. Clear? Clear? Why am I doing this? To prevent my filter from clotting and my efficiency of the filter from going down. Right? Because the filter clots, pore size gone, no pores, no diffusion, no convection, efficiency will fall. Are you understanding? That filter has to be maintained. That is the entire problem. Okay? And that is why I will want to keep it at this situation. Clear? Now what happens in this modality? Where you have this equation already in place, 2.5 into QD, and you have the other one where when you have QB is equal to more than 6 times Q replacement. You have both here. So you take the larger. You take the larger of the equation. Okay, whichever is the larger variety. We'll come to it. Can it be 1,000 only? This can be 4,000. This can be 1,000. We'll come to why you might change later on. We will take a scenario. So, but we will take the larger of both these. The larger one. इसमें और इसमें जो larger है, we will take that one. Clear? Clear till now? Is it clear? Simple? It's not difficult. Not difficult at all. Right? You've understood what is effluent. You've understood what is dose. You've understood what is how to calculate the dose. You've understood how to maintain your blood pump, at what speed to keep it, so that you ensure that the filter does not clot. You've understood these things? Now let us go about all this filtration business, this problem that is occurring. Okay, so how do you calculate this? So on an average, if you see the ones that I am using, there should be no filter clotting. If you look at 1,000, 150, it is not going to clot my filter. Conventionally, it is not going to clot, it is going to preserve the efficiency. Clear? So, but somebody asks you, what is the filtration fraction? You should know what is the filtration fraction. What is the filtration fraction? So, let's go back to our diagram. Okay, let's go back to our diagram. I am again drawing you the same thing. Okay. So, this is my filter. This is my blood going inside. This is my blood coming outside. And this is what is filtering outside, which is called as Q. Right? Simple. Effluent, I put my effluent coming from here. I put my replacement fluid going from here. So in my CVVH modality, this is my blood going inside. My pre-filter replacement has gone here. My post blood is coming out from here, and my effluent is coming out here. In anything, what is the filtration fraction? How much comes out? how much comes out is a filtration fraction, isn't it? Huh? So let me put this as QEEF from how much blood it has come out. This is my filtration fraction. Huh? Means I will study the amount of flow that has come in from here and divide it with my blood. That is the amount that is filtered. This is my filtration fraction. Somewhere, right? Huh? I may want to add urea nitrogen here, but both will get cancelled. No? I want the amount. The amount is what? Urea. Amount is what? Urea. I can monitor the urea. But what did I say? It's a slow modality. At 12 to 24 hours, the urea in the blood and urea in the effluent will remain the same. So if I put it in that equation, it will cancel out. How much is filtered? How much urea am I filtering from here is what I'm asking. How much urea I'm filtering from here is equal to the filtration fraction. Right? समझ में आ रहा है? Since I know that at 24 hours, my urea going from here and urea coming here is the same, I can actually just equate this equation as QEF upon QB. समझ में आ रहा है? Effluent upon blood. Clear? Understood this much? समझ में आया? Simple है ना? Filtration fraction. Now, it is not so simple also because here I am looking at the plasma flow inside this. So my QEF, now you know what is QEF, you know the flow. If it is CVVH, it is QR plus UF. If it is CVVHD, it is QR plus QD plus UF. If it is just CVVHD, no without UF, it is QR plus QD. You know what is the effluent. You know that calculation. Now I want the plasma here. What is the plasma? QB 1 minus, that's my plasma. Remove all the cells from inside the blood, that's my plasma. What is my cells? Hematocrit. You understand? Huh? I'm removing the cells from the plasma by removing my hematocrit. What is it? Hematocrit is in percentage, no? So I'm removing 1 out of the hematocrit percentage. Right? Huh? And I have my filtration fraction. At any given moment, my filtration fraction should not be more than 20%. At any given moment, my filtration fraction should not be more than 20%. So, if my filtration fraction goes above 20%, my filter will get clotted. Now, let's take the example of one of our patients. Let's put 1000 plus 1000. And let's put 9000 here. That's my blood flow rate. And let me take the hematocrit as 30. So it's 70. Or 30 means 3 to 0.7. 0.7. So this is 7 9 is 63. 1100. So it is not more than, it is less than 20%. Are you understanding? So at any given moment, my filtration fraction should be more than, cannot be more than 20% filtration fraction. Clear? Clear on this? Clear? Simple? It's actually very simple. Filtration fraction, it's actually very, very simple. Clear on this? With this now, it is enough for you to run CRRT, if you ask me. With this much, of course, I can go into what happens when there is hypernatremia, what happens when there is hyponatremia, how do you manage it? Because UF is only fluid. UF is only fluid. The rest we can come one by one. I don't want you to push too many things into your brain. We have understood some basics of CRRT. Now let me give you now let us tweak it a little bit, and I'll give you a case scenario. Okay, I'll give you a case scenario now that you understood what happens with diffusion, what happens with convection. What happens with what about combined modality? I'll give you a case scenario and you tell me what are you going to do. Okay, so I have a patient who comes in with hyperkalemia of 6.1 and acidosis of 7 bicarbonate and he's hemodynamically stable. But this bicarbonate is 7 and his potassium is 6.1. Potassium is 6.1. And his bicarbonate is 6, he is slightly unstable I'm unable to institute intermittent hemodialysis because of this hemodynamic instability that is there, not very stable. Huh? What will I use? Which modality I'll use? Why? And how do you think you should use this now? Let's put up a dose. Okay, the dose has to be what?
35.
Dose has to be that. Dose has to be 25 to 35. Chem 25, chem 35. Okay. Now you tell me what modality, Nikhil, what modality you would like to use here? You have got 3 modalities in front of you. I can put one more for you. I'll put scuff also here. Slow continuous ultrafiltration. Now you understand what is ultrafiltration? It's just removal of water. Okay. Which of these you use?
Use CVHD
And why do you want to use that?
because we want to filter out the ions for basically potassium and bicarb that can be removed by concentration gradient.
So that means you have only diffusion.
Yes.
But this patient is having severe acidosis. The modality is slow. 6.1. You agree to this what I'm saying? Huh? The modality is slow. You must remember this CRRT modality is slow. That means it's going to take a while before we actually get back to normalcy.
Yes.
Right? So you would want to do what?
DHF.
Yes, I want to increase my efficiency. So what will I use?
Both are DHF.
I will want to use both. First, this is clear from all of us? That I want to use both? Huh? I want to use both, that's clear? बाद में बात करूँगा. Huh? बाद में करूँगा. Huh? Clear on this? I want to use both. Now in that both, you agree that I want to put QR and you agree that I want to put QD. You agree this much? This is going to be my modality. Huh? CVVHDF. This is my modality. Clear on this? Huh? Now, as you rightly said, which is the maximum effect I'm going to get on?
H wala. VH.
You're right, dialysis. The maximum is not going to be filtration.
Yes.
The maximum is going to be dialysis because diffusion से सबसे ज़्यादा move convection से नहीं आएगा ज़्यादा. Convection is for small and middle, but the maximum molecular movement is going to occur in small molecules by diffusion. By diffusion. So then in my equation here, I want to put, because I put these things, I have to put 4 things. I have to put blood flow. I have to put dialysis flow. I have to put replacement flow. These 3 things I have to put. No, whatever happens, I have to put these 3 things. I am not concerned with fluid overload here, so I don't need to put a UF. My UF will be 0. I don't require it. So in this scenario, I want my dose also to be good. At the same time, I want the diffusion to be maximum. So which of these will be maximum? So I will keep my QD, say 3000. Say I keep 3000. Let me keep it as 3000. Okay. And I also want that there's some convection to occur also. So maybe I'll put this at say 2000. Because I want it fast. Because this is the problem. I want it really fast, isn't it? So I want my efficiency to be on the maximum. That means my dose has to be high. At the same time, my diffusion modality has to work maximum. Now calculate my blood pump, how much it should be. So let's put it up now. So when I'm actually using dialysis, what should be my blood pump? 2.5 times.
So we will be using
CVVHDF.
So it will be either
2.5 times the
QD or 6 times of QR.
Yes.
Whichever is greater. So we will use this one.
No, which is greater? You write down.
Yeah.
Write down which is greater. 2.5 into 3000 karo.
5 into 3000.
Is how much?
So
7.5. 7,500.
7,500.
Okay, 7,000. Now you do 6 into QR.
6 into
12,000.
12,000.
Which is the larger one?
QR.
Which is the larger one?
QR.
And the QR has to be 6 times. Now you have to use the 6 times of equation because QR is larger. So what is 6 times? So divided by 6, no?
हाँ.
Divided by 6 कितना हो गया?
2000.
2000. Again you divide by what?
60.
60 minutes. Right? करो 60 कितना हो गया?
So around 36.
33.
This is your dose. What should be your pump flow? ml per minute?
Yeah, ml per minute.
How much should be ml per minute?
So into 60 again.
How much should be ml per minute here? This is your dose.
Dose.
ml per minute? See what have you done till now?
60 again, no?
Into 60 again.
Into 60.
So this is
1200. Yeah.
what is your dose here? Your total is here Q
77,000.
R into 7 is, so QB has to be 7 times that of 6 times that of QR. This is what I have to use now. This is what I have used. Okay, 6 times QR is how much?
12,000.
12,000
This is per hour.
ml per hour. So 12,000 ml in 1 hour. Okay, 60 minutes. So per minute is how much? So 12,000 divided by 60.
200.
6 2s are 12. So what is my blood pump flow?
200 ml per hour.
So ma'am,
Minute.
understood?
Per minute.
200 ml per minute.
Not per kg also.
No, blood pump is ml per minute.
Per kg
This
is 33 wala.
ml per minute.
Yes.
What is my efficiency now? What is my dose I'm giving? Come, Vidya, what is my dose? Write down the dose. Dose कितना दे रहा हूँ मैं? This is my
Blood flow.
this is my blood pump flow. I have written my blood pump flow is 200. Now I have added this. मैंने इसको add कर दिया इधर 200. This is my prescription.
Yes.
For my patient. Now you write the dose. What is the dose here? Dose. Dose is what? Dose is what? 25, 35. What is that?
ml per minute.
What is that?
Effluent that comes out.
Comes out. That comes out. What is coming out here?
Total dialysis plus replacement.
हाँ कितना है total करो अभी?
7,500.
5,000. 5,000 and this is you have to do it per
Per kg.
per kg. Now kg take it as 70 कितना हो गया?
70 per hour. 70 per kg per hour.
70. No.
हाँ 49 हो जाएगा 70 लाख हो जाएगा.
70.
70 ml per kilogram per hour. That is the dose you are giving to this patient. समझ में आ रहा है? Such a high dose you are giving. So when I am doing emergency dialysis or for this patient, I am giving very high doses to affect this. समझ में आ रहा है? सचिन समझ में आया तेरे को? समझ में आया? Clear?
But ये केस सिनेरियो में ऐसे hemophiltration how it is working? Dialysis I got it.
So convection also clears small and middle molecules. So small molecules भी निकलता है. Now this is a very difficult scenario because I ideally want to do intermittent hemodialysis.
Yes.
Are you understanding? Because potassium high है उसका, potassium high and bicarbonates are very low. I actually want to do intermittent hemodialysis.
फास्ट निकलना पड़ेगा.
लेकिन मेरे को possible ही नहीं है with my CRRT machine. So I want to optimize whatever I can. मेरा dialysis is only 1,000, 2,000. Imagine a nurse taking 3,000 ml per hour. So she will be changing bags. You know, so fast. 5,000 का एक bag आता है. So within 1 hour she'll be changing this bag. Within at second hour onwards she'll be quickly changing bags. Are you understanding? 3,000 ml. I want to increase my as much as possible. मेरा मन चाहूंगा तो मैं इसको 6,000 रखूंगा. इसको मैं 6,000 रखूंगा. 6,000 ml per hour. क्योंकि then my diffusion capacity will be maximum. There is no high level. But what happens as you go higher and higher? Your filtration fraction will start increasing, which we have discussed. A filtration fraction is actually a figment of effluent flow upon blood pump flow. Right? Now, when I go up on this, my effluent is going to go up. If my effluent goes up, my filtration fraction will increase. Are you understanding? समझ में आ रहा है? तो इसको मैं अगर समझ इसमें डाल दिया इसमें, so if I put 3,000 plus 2,000 is 5,000. That's my effluent. And my blood pump say I catch it as QB. As maybe I forget the hematocrit. Just let's put the blood pump. Okay, कितना होगा ये? 200. 200 of 5,000. Okay, ये फिर भी ठीक लग रहा है. कितना लग रहा है? 25. So it's high. More than 25%. Are you understanding? I have a problem. You understand? Filtration. That's why it's a problem to do such high volume therapies. समझ में आ रहा है? So somehow I want to increase my amount of diffusion. That's why I'm doing it. Now let's give another example. Okay, I'll give you another example. Any questions?
So how
Simon?
do we decide dialyzer fluid like replacement QD and QR?
Just thinking now. See, on an average you're thinking, it's after all, मैं करने के बाद I will repeat after 4 hours. क्या होगा पोटेंशियल को? 4 घंटे के बाद पोटेंशियल देखो क्या हुआ, 6 घंटे के बाद every 12 hours we'll keep repeating. Oh ऐसा हो गया, ठीक है अभी ऐसा हो गया. This is not the modality I want to use. At the same time, what I'm going to do in this case, I want to do it so fast. I want to do it very fast. That is why my replacement fluid will initially have maybe 0K. Keep 0 potassium on the replacement fluid because I want the convection to occur. My dialysis will also be 0K. I'm going to do that, but I'm going to quickly follow that up because it is very dangerous to keep 0K because अगर जल्दी अगर हो गया तो पेशेंट को पोटेशियम 0 हो जाएगा, मतलब 1 2 हो जाएगा, समझ में आ रहा है? 1 हो जाएगा, 1 या 1.5 हो जाएगा, पेशेंट कैन अरेस्ट. You understanding? So I'll probably do 0K, but 2 hours later I will check क्या पोटेशियम आ रहा है to see what is the trend. समझ में आ रहा है? You understood? Now you were asking, no, how I am determining this? It depends on my dose. I want to give 35 ml a kilogram per hour. That is my dose I want to give. So I am going retrospectively what I want, which part of the therapy I want. Do I want convection? Do I want diffusion? Do I want UF? Based on that I am taking my entire call. Okay, you understand? So on conventionally starting point 800 बोलिए चलो, because 25 ml per kilogram अगर पकड़ा मैंने 25 ml, so say 800 plus 800 is 1600. Now in 1600 if I divide 1600 by weight of say 50 kilos, कितना आता है ये?
33.
That's pretty normal. 800 and 800. So that's my starting point. It's actually low. It's actually high. 25 is enough. 800 is enough. You got the point? Now let me give you another scenario. Okay, I'm cutting up all of these things. Okay, I got to give you again what to do with these things. Okay, so now I'm going to give you a situation where there was a road traffic accident. Okay, there was a road traffic accident, and now this patient has come into the ICU and he has got severe myoglobinuria. CPK is 60,000 and he's gone into ATN because of severe myoglobinuria. ATN, severe myoglobinuria. Now what will you do? Severe myoglobinuria. Which modality will you use? CVVH, CVVHG, CVHGF and Y. Myoglobin is what size molecule? So what do I want to use more?
Convection.
You understand? So I want to use convection more. So in this case, maybe I will increase my convection dose here. So replacement fluid I will increase. Maybe I'll make the replacement 2000 and I'll keep my dialysate as 1000 or 800 or whatever lower I want. You understand? And accordingly I'll keep my blood pump flow, which on an average if you keep 150, I have 9 liters. I know when I keep my blood pump at 150, I know my entire replacement is going to be look at this 6,000 or 2,000. Okay, so 2,000 into R is how much? Into 6 is how much? 12,000. 12,000. 150 ml per minute, no? 150 into 60 is how much? I have a problem. I have a problem. Clear problem? विद्या समझ में आया? 150 ml per minute में रखा था? Is my dose right? Why? Not filtration fraction. Of course, filtration fraction will increase. Why? Because my first tenet is I want to keep my blood pump 6 times that of my replacement fluid. 6 times of my replacement fluid. This is my first thing to prevent filter clotting. Right? 6 times my replacement fluid. My replacement fluid I started at 2000. So 6 times 2000 is 12,000. And I have kept my blood pump at 150. 150 ml per minute is equal to 9,000 ml per hour. This is more. So is this enough? I will need to increase that. So maybe I'll make it 200. Let's see. 200 kiya. 200 to 60 हो गया? Just equal. Just equal. So I'll probably require a higher dose of blood pump, maybe 250 ml into 6. So this is the problem. So when you're going higher and higher on your blood pump flow, there is going to be more and more problems. Okay, based on hypotension, hemodynamic embarrassment. So in myoglobinuria, sometimes you may want 2 CRRT machines. You know, you require 2 CRRT machines because you just can't go too high. So you have 1 CRRT on this side, 1 CRRT on this side, both do the same thing. Are you understanding? Huh? So when you have very severe rhabdomyolysis, for example, snake bite, very severe rhabdomyolysis you have very high myoglobins. You may actually require 2 CRRT machines because you just can't optimize otherwise. And whenever you're doing this, you will also write your filtration fraction. You'll also write your filtration fraction. You'll also write your filtration fraction saying that okay, my filtration fraction is adequate. So usually your filtration fraction will be adequate when you follow that 6 into QR and 2.5 into QD. When you follow that, usually your filtration fraction will be good enough. Right? Clear?
So what if we decrease the replacement fluid?
Then your convection will be decreased and then your myoglobin will not come out. At the end of the day, you are actually doing a titration. You are doing a titration. So uske baad you are repeating to see what is happening. If you reduce the convection, the amount of flow will reduce, the myoglobin coming out will reduce. Simple. Myoglobin comes out, that is our main thing, to get the myoglobin out. You will not be able to take it off. Samajh mein aaya? Any queries?
So maybe like proportionally then the convection will remain same. If the fluid is, if the blood flow, if we are keeping it 150 and just for example we are taking down the replacement fluid flow, then proportionally for the what blood flow is going through the pump, for that the convection will remain same.
Yes, it will remain the same.
So even if like instead of increasing the blood flow, we can go down a bit on replacement.
So we don't know what happens. So we exactly, if you ask me in the micromanagement what happens, we don't know. But we know this way that if you increase the convection, the myoglobin will come out. We know that. So on broadly, if I have rhabdomyolysis, I will keep my convection high, my dialysis low. Broadly, if I have acidosis and hyperkalemia, I will keep my dialysis high and my convection low. Broadly, if I have everything together, I will keep both equal. And then see what I want to do. You understand? It's as simple as that, That's why for me it tends to be 150,000. Unless there is something that is very critical and I need to change things, then I would probably use something else.
So the blood flow, like maximum how much we can go, like because depending
the blood pumps, so it varies from various machines to machines, but you can go up to 450.
450.
Yeah, you can go up to 450. Many of these machines give up to 450 ml per minute. They give 450 ml per minute.
It's in CRRT that this much flow is not allowed.
Not allowed. He asking how much you can go. You can go so much, but not allowed. It will become dialysis. If you can do 450 ml per minute,
fast.
you will do dialysis. Why you want to do CRRT? Are you understanding? Agar 450, if you can afford to do 450, this patient is not a candidate for CRRT. This patient you can manage to dialysis. You are understanding, no? I will not want to use that. I will not want to use that at a higher amount. You understand? So now, tomorrow if your TMP goes up, that is a membrane is becoming more and more clotted. You are going to keep a watch on these membranes. Now you understand what is happening. Filtration fraction you can figure out, and you can understand this is what is happening. So now you will understand why it is pre-filter. When you do this same thing post-filter, we are doing this here, no? We are doing this here, pre-filter. If by any chance you put this post-filter, we discussed, no? If you put it post-filter, the efficiency actually comes down a little bit. Efficiency goes up a little bit. Since the efficiency goes up, what will you do with the blood pump? The blood pump now becomes QB 5 into QR. You were asking this question sometime back, that's why I said. So what happens is, if you have, if you want to place your replacement fluid after the filter, obviously the efficiency is going to go up, right? Efficiency is going to go up because that much amount of blood is actually going without getting diluted. So at that time you require a lower blood pump flow, which is around 5 times that of the replacement fluid. This is for post-filter. Post-filter replacement. This is for pre-filter replacement. Understood? Understood this? With this, you can manage anything. With what I have done, you can manage anything. Now,
5 times. Blood flow pump बढ़ गया 5 times तो like
कम हो गया ना? पहला 6 times था,
हाँ.
अभी तो 5 times दे रहे हो replacement fluid का. You understand? And why are you reducing it? Because actually blood is going without getting diluted. So I don't really require so much of flows. समझ में आ रहा है ना? It's going without diluted, so you don't require so much of flows. So by doing this much, no, you will be able to do most of your CRRTs. Most of your CRRTs you can manage. Now, I don't want to go into the specifics of a lot of other things, which includes how to manage this electrolytemia, because that will become too much for you today. Okay, it will become too much for you. We will hold CRRT at this. I don't think you require anything more than this, at least for practicing CRRT. Huh? For practicing CRRT, I don't think you require anything more than this. Okay. However, when we come to a condition where we are doing CRRT and we have it on, you must first understand this much, and then I can go to the higher level of CRRT, where advanced CRRT, where what to do when you want to give 3% saline. What to do when the sodiums are 170, what to do when the sodiums are 112. That is a different ball game, no? What to do when there is hypotension, we'll do next time. What to do when there is hypotension, we'll do next time. As of now, this much you should know. So the next time when we meet, I'm just going slowly so that you understand everything, okay? Otherwise, बहुत ज़्यादा हो जाएगा. Okay? So the next time when we meet, you can stop this up.